Now that we've discussed u-substitution, we want to go ahead and introduce, of course, the exponential and logarithmic antiderivatives and how to do u-substitution with these very important functions. These functions describe everything from cell growth to population growth, radioactive decay, financial growth, depreciation, resource consumption. There are so many applications of exponential and logarithmic equations. They truly are some of the most important functions for the real world applications for which we use calculus. We only have two real learning objectives in this particular video, and that is to integrate using exponential functions and to integrate using logarithmic functions. So it's pretty straightforward, and this will be a relatively short video. Let's go ahead and get started. Let's go ahead and remind ourselves, we'll start with the exponentials, but let's remind ourselves what the derivative of an exponential function is. Remember, an exponential function is a constant, a positive constant, and not one that is raised to some variable expression. In other words, the variable is in the power, but the base of it is a positive constant, not one. You restrict this in order to provide a continuous graph. When we take the derivative of e to the x, probably our favorite function to deal with, the derivative is e to the x. That's why it's one of our favorites. If the base is not e, Euler's number, then let's say it's 5 to the x, then the derivative would be 5 to the x again times the natural log of 5. Now, the reason we don't have that in the derivative of e to the x is that the natural log of e is the number 1. So in essence, it is the same formula. It's just that the natural log of e is the number 1. Now we want to undo this. As you know, in mathematics, we learn to do an operation, then we learn to undo it. So in order to integrate an exponential function, the integral of e to the x dx, the indefinite integral, would be the antiderivative function e to the x up to the constant plus c, giving us a family of antiderivative functions. When we integrate an exponential function with a base other than Euler's number e, well, then we have to take into account the fact that we're not starting with b to the x natural log of b, meaning that we're missing this natural log of the base. So when we integrate, we get the exponential function divided by the factor that was not present in the integrand. So we get b to the x divided by the natural log of b, again, plus the constant of integration. Do not make the mistake when dealing with exponential functions of treating them like polynomial expressions. You cannot apply the power rule to an exponential function. Remember that when you have a power function, you have a variable raised to a constant power. And when you have a power function, then you can apply the power rule. When you have an exponential function, the locations are reversed. An exponential function is a constant raised to a variable power. Very different functions, different operations. Don't mistake one for the other. And remember that Euler's number e, while it is special, is still just a constant. It's about 2.7182818288459. It is an irrational number. There's no pattern, and it never stops. Let's go ahead and integrate using u-substitution in example 1. We have the indefinite integral of 2x cubed times the exponential function e to the x to the 4th power with the differential dx. Remember that when we're looking for expressions to be u and we're dealing with an exponential function, the power expression on the exponential is where we typically look to find u. That would make x to the 4th u. I also know that when I take the derivative of x to the fourth, I'll have a multiple of x to the third. And I have a multiple of x to the third as a factor in the integrand. This gives me confidence that I'm choosing the correct u by choosing u to be x to the fourth. Let's go ahead and make that substitution. If I let u be x to the fourth, then the next thing I want to do is find the derivative of u with respect to the differential. The original differential is what we're taking the derivative with respect to. In this case, du dx will give me 4x cubed. Then I abuse the notation and I swing the differential in the denominator around to the other side. This gives me an expression for du. 4x cubed dx. Now, what you do from here, of course, depends upon the way that your brain operates and kind of how you think. You can either solve for just the differential dx and do a substitution for dx in the original integral, or you can look at the original integral and recognize that you have x cubed dx, but not the 4, and you could solve for x cubed dx and then substitute for that part. This is totally a matter of preference. In my case, I'm going to go ahead and I'm going to solve for the differential dx. This will give me du divided by 4x cubed. The next thing I want to do is I want to substitute in the original integrand. So I had 2x cubed e to the x to the fourth power dx. And I'm going to replace the e to the x to the fourth with e to the u. And I'm going to replace my dx with du divided by 4x cubed. This means that the x cubes will cancel, and I will end up with 2/4 or 1/2 e to the u du. Now, the 2/4, of course, reduces, and I can also factor that out of the integral because it's a constant. So if I take the integral out, this will give me 1/2 the integral of e to the u du. This is factoring out the constant factor. And the next thing that we do is we go ahead and integrate, find the antiderivative function, which is e to the u, up to that constant plus c. Now remember, when you're doing u-substitution, that you have to back substitute to get back to the original variable. In our original indefinite integral, we were using the variable x. That, in an indefinite integral, is the variable you must end up with. In a definite integral, you're getting a number, so it's different. But in an indefinite integral, you're getting an antiderivative function. So the final variable must match the variable in the original indefinite integral. So we back substitute, again, using our substitution equation, and we get 1/2 e x to the fourth plus a constant. And this becomes our solution. Let's now move on to example 2. Looking at example 2, we first want to recognize whether we have a definite integral or an indefinite integral. We'll still be looking for an antiderivative function, but this tells us whether or not we're going to have to return to the original variable or if we can completely switch over to u. In this case, we have a definite integral, so we're looking for a constant solution. We're looking for one number, which represents the area between the independent axis and the curve e to the 2x between x equals 0 and x equals 2. Since we're looking for a number, we will not have a variable in the solution, so we can completely switch over to the u form. Again, we're looking to have u be the expression that we have in the power on the exponential. Since u is equal to 2x, we take the derivative with respect to the independent variable and get 2. Then we abuse the notation by swinging the dx around. And again, this is an abuse of notation, but it works, and so we do it. Okay. Then we solve for dx, which gives us du divided by 2. Now, because this is a definite integral, we want to replace the limits of integration. Some students prefer to back substitute, but it is more work and more likely to create errors. There are a few situations where it's not ideal, but for the most part, it's best to switch completely over to u and not return to the original independent variable when doing a definite integral. In this case, we're going to go ahead and change the limits, and we're going to say that when x is equal to 0, we're going to use our substitution equation, then u is equal to 2 times 0, which equals 0. When x is equal to 2, u is equal to 2 times 2, which is equal to 4. Now that we have changed the limits, we can rewrite the original expression, but in terms of u. So we're taking the original integral from 0 to 2 of e to the 2x dx, and we're replacing what was an x equals 0 with a u equals 0 up to 4 of e to the u, and then I substitute for dx, du divided by 2. Now, again, the 1/2 is a constant, so I can factor the constant out. After I've completed the substitution, I'm going to go ahead and I'm going to replace or put the constant on the front. So I have 1/2 the integral from 0 to 4 of e to the u du. If you choose to keep the original limits of integration, then you must write x equals 0 and x equal 2 when you have rewritten the integrand and the differential in terms of u. If they do not match the differential, then you must write what the variable is in the limits of integration if it doesn't match. Now, finding the antiderivative function, I get e to the u. But because I'm doing a definite integral, I choose the antiderivative with a constant of 0. These are u values, 0 to 4, so I can go ahead and substitute those into the final solution. In this case, I like to keep my constant factors on the outside, and then I substitute the upper limit of integration into the antiderivative and subtract what I get when I substitute the lower limit. Remember, e to the 0 is not 0, it's 1. So for a final answer, I end up with 1/2 times the quantity e to the 4th minus 1. And if you like, you can go ahead and distribute that as well. Now, this is in fact a constant. When we're looking at this, this represents that area between the curve and the independent axis. So let's take a look at the picture and see what we actually just computed. Here's the graph of e to the 2x, but only between 0 and 2. I've shaded that region right here. And what we got was the area between the curve and the independent axis for that function. So what we computed, that 1/2 of e to the 4th minus 1, is the area of that blue shaded region. Let's take a look at this particular exponential. Again, we have a definite integral, so we're looking for a constant value answer, which means that the best approach is to completely switch over to u and never come back to x. Because we have an exponential function, we look for u to be the power expression. In our expression, we have 4x to the negative 2. And when we take the derivative of it, we would get negative 8 x to the negative 3. X to the negative 3 is 1 over x cubed. I do have a 1 over x cubed as a factor in the integrand. That gives me confidence that I've chosen the right u. Go ahead and pause the video, work this one out, and then turn the video back on so we can compare our results. So let's see how you did. In this problem, I identified that it was u-substitution, and I made the choice that u was the expression in the exponent of the exponential function. Then I take the derivative with respect to the independent variable, making sure that this differential in the original integral matches the derivative that I'm taking of u. When I take the derivative with respect to x, I get negative 8x to the negative 3, which is negative 8 over x cubed. Make sure you don't send that negative 8 to the denominator too. It has its own power, which is 1. Then I abuse the notation by swinging the differential dx to the opposite side. Now here again, you have a choice. We need to solve for something in order to substitute back in the original integral. I have 1 over x cubed dx. So in this problem, I chose to simply move the negative 8 by dividing both sides by negative 8. That left 1 over x cubed dx to be replaced with du divided by negative 8. That will take care of this part of the original integral. And I will substitute u in place of the original exponential power. Next, I want to change the limits of integration because it's less work and less likely to create error. I use my substitution equation, which is up here at the top. And I can also write it in the form of 4 divided by x squared, which makes it easier to compute the new limits. When x is 1, u becomes 4 divided by 1 squared, which is 4. When x is 2, I get 1. Be sure that you write these in the order that they are in the original problem. When x is 1, it's the lower limit of integration. So the 4, though it is the larger u limit, goes in the lower limit of integration. And the 1, even though it's the smaller u limit, is going to go in the upper because it is replacing x equal 2. When I look at the new integral, I want to go ahead and I factor out the 1 over negative 8. Now, I personally don't like to leave negatives hanging around if I can easily get rid of them. Because my limits of integration are not in the order I expected, I know that if I reverse the limits of integration, it will throw in another negative, which will give me a double negative and make this a positive. So I chose to change the limits to eliminate that negative. That gave me the positive definite integral of 1 over 8 times the integral from 1 to 4 of e to the u du. Antiderivative function of e to the u is e to the u. And I choose to have the constant be 0. Then I evaluate between 1 and 4. And you could distribute the 1/8, but you can also leave it out. Now, again, what does this represent? This represents the area between the original curve and the independent axis between 1 and 2. You can see the graph of the original function that was in the integrand, 1 over x cubed e to the 4x to the negative 2 power. And you can see that I've shaded in the region between 1 and 2. Now, it's a really tall, narrow object here, but the area that I got is that 1/8 times e to the 4th minus e. We have one more example that I want to work, and then we'll look at logarithms. In this particular example, we're looking at an exponential function where the base is not Euler's number. It's our favorite to use Euler's number because the natural log of e is 1, so we don't have to worry about that added factor. In this case, we will. We should have a natural log of 3 in the integrand, but we don't. So when we integrate, we'll end up with a 1 over the natural log of 3. Go ahead and pause the video, work it out, then turn the video back on so we can compare results. When we look at this integral, first note that it is an indefinite integral. The differential is dx, so the independent variable is x. We're looking for an antiderivative function up to a constant plus c. We will have to return to the variable x for our final solution. There's no switching to u completely. Again, I make the choice that u is the expression that represents the power on the exponential function. U equals negative x. When I take the derivative with respect to the original differential, I get negative 1. I abuse the notation by swinging the differential dx to the opposite side, and then I solve for dx in order to substitute this back into the original indefinite integral. When I substitute, I get the indefinite integral of 3 to the u power times negative du. The negative is a constant negative 1, which can be factored out of the indefinite integral. Then I integrate, remembering that the antiderivative of an exponential is the exponential divided by the natural log of the base, in this case, 3. This gives me negative 3 to the u divided by the natural log of 3, all plus the constant of integration. Because I am getting a family of functions, I must return to the original variable in the original differential. You can see why the differential is so important. Now we back substitute and replace u with negative x. And this gives us our final antiderivative function up to the constant plus c. Now we want to switch gears and we want to talk about logarithmic functions. We've dealt with the exponentials and how to do u-substitution. Let's now talk about the logarithmic functions. We're going to start by going over the derivative of natural log again. Derivative of the natural log of x is 1 over x times the derivative of the argument to natural log. The derivative of x is just 1, so we get 1 over x. But in general, the form is the derivative of natural log of u is 1 over u du dx. This u form gives us some information about how to reverse the process. When we want to reverse the process, this basically means that in the function that has some multiple of 1 over x inside the integrand must result in a natural logarithm. When we look at the natural logarithm, though, remember that logarithm has a very restricted domain, must be strictly positive. And so we have to put whatever is in there inside absolute values. Let's now look at the rule for integration. When we integrate 1 over x dx, we don't get the natural log of x because x could be any value. We must force it to be strictly positive by taking the absolute value of it. And of course, this also implies that x cannot be 0 because natural log of 0 is not defined. So the indefinite integral of 1 over x dx is the natural log of the absolute value of x plus the constant of integration. Yes, most professors are very picky about those absolute values. Leaving them off is not a minor error. The next two are actually formulas that you're going to prove when you get into Calculus 2. In order to prove these, you will need something called integration by parts, which is a technique for integrating when you have functions in the integrand of different types. In this case, for now, you can just go ahead and memorize the form if you want to, though I don't expect my students to have this memorized in Calculus 1. I do expect them to be able to prove it in Calculus 2 and often ask for it on exams. The integral of natural log of x dx is actually x times the natural log of x minus x plus c, again with the understanding that x must be strictly positive. If the base is something other than Euler's number e, so that we don't have natural log, we end up with pretty much the same function, but we have to divide by the natural log of the base since it wasn't in the original integrand. Most of our work will involve the first formula, though you might see the second one pop up occasionally in a homework problem. Let's now turn our attention to example 5. In example 5, what we want to do is we want to find the indefinite integral of the natural log of x divided by x dx. This means that we have to find a u. It's an indefinite integral, so I'm looking for an antiderivative function up to the constant of integration plus c. I'll have to return to x. I can't stick with u. When I'm looking at something like this, it is generally the case that natural log is going to be a part of u. In this case, if we choose natural log of x to be u, we know the derivative is 1 over x, and I do have a 1 over x in the integral. In other words, it might be helpful if you were to think of the original problem as 1 over x times the natural log of x with respect to x. And then you can see that natural log of x could be u, and the factor 1 over x is du. Let's go ahead and set up the problem now. In this case, we're going to choose u to equal the natural log of x. We're doing u-substitution on this indefinite integral. And we take the derivative with respect to the original differential. When we take the derivative of u, we end up with 1 over x. Next, we abuse the notation and swing the differential dx to the other side of the equation. Finally, we look to see if we want to substitute or solve only for dx, or if we can leave it in the form that we have. Because I've rewritten it in this form, I know I can replace the 1 over x dx with du. In other words, I'm replacing this part of the original integrand. I'm substituting that for this du here. And for natural log of x, I will substitute u. Let's go ahead and write down what we would get. This becomes the integral of 1 over x, natural log of x, dx. And when we substitute, I get the natural log of u times du. After I've substituted, oops, not natural log of u, just u, I get u du. Now that I have u du, I can integrate. When I look at u du, I've changed the format from being something related to natural log to something that is, in fact, a polynomial. This is just u to the first power du. So I can apply the power rule for integrals. When I apply the power rule, I add 1 to the power, divide by the new power, and I get it up to a constant. So I integrate using the power rule. Next, I have to back substitute. I have to leave the indefinite integral in terms of the original variable, which in our case is x. So when I back substitute, I get the natural log of x, which replaces my u, squared, all divided by 2, plus a constant. You must return the indefinite integral back to the original variable. Now, when I'm looking at this one, there are a couple of ways that you can write it. When you're looking at the natural log of x, quantity squared, You can sometimes, and we do sometimes, put the 2 between the natural log and the x. However, I don't particularly like this notation. I think it tempts students to think it's natural log of x squared instead of the natural log of x quantity squared. So I prefer the parentheses. Let's now take a look at the last example, example 6. Again, we have an indefinite integral, so we know that we'll have to return to the original variable, which is x. In this case, again, we have a mixture of natural log and some algebraic functions. In this case, we have natural log inside parentheses and squared, and it's also in the denominator. Natural log of x, when present in the integrand, is often a part of u. And in this case, I again think that probably natural log of x by itself is the u because it's being raised to the power of 2. Let's see if we can rewrite this one in a different format that might make that clearer. I'm going to separate the factor 1 over x from 1 over the natural log of x squared dx. Next, I'm going to rewrite this 1 over natural log of x squared as the natural log of x raised to the negative 2 power. This makes it a little bit clearer that natural log of x should be our u, and the 1 over x is our du. Go ahead and pause the video, work this one out, and then come back so that we can compare our results. So let's compare our results. I set u to be the natural log of x. I took the derivative with respect to the original differential to get 1 over x. Again, the u-substitution gives me 1 over the argument times the derivative of the argument, which is just 1. And I abuse the notation by swinging the differential around. And because I can identify the 1 over x and the dx in the original integrand, I can substitute for these factors using the du. And I can also substitute the natural log of x with the u. Then, when I substitute, I replace natural log of x with u to get u to the negative 2, and I replace the factor 1 over x dx with the differential du. Then I integrate using the power rule, since this is actually an algebraic function. I add 1 to the power and divide by the new power, which gave me u to the negative 1 divided by negative 1. I rewrote this as negative 1 over u plus a constant, and then I back substituted to get back to the original variable, which is x. Make sure you don't forget to add on the constant of integration. This is actually the end of this video. I know it's very short. In our next video, in the last section of chapter 5, we'll take a look at how to integrate with those inverse trig functions. Then we will have completed our initial study of integration. We'll expand our study of integration in Calculus 2 when we learn techniques to deal with products in the integrand and quotients in the integrand. Join me for the next video.